Dear students, welcome to another video session on the topic called race condition. Okay, so today we'll be seeing race condition and we'll be studying about critical and non-critical race. So before going to what is race and critical and non-critical conditions or races, I'll just take you all to the basic block diagram of asynchronous sequential circuit. Okay. So let's see the block diagram of asynchronous sequential circuit. Okay. So we know that a combinational circuit, right? So what is a combinational circuit? It is made up of gates, right? So here is the combinational circuits. I can say that it consists of group of gates, correct? So you'll have several inputs. So let me tell, these inputs are say n inputs, okay, and you will have several outputs. So let me name this as m outputs, okay. So apart from this, so let me consider something as the excitation variables which has a delay element, okay. It is a sort of a feedback which has a delay element and which will be fed back, okay. So this is the excitation variables. So let me consider one other excitation variable which consists of a delay element and it will be fed back, right? So let me consider this as something, let me name this as capital Y1, okay, and we will have n number of variables, and let me name this as capital Yn, and these excitation variables, let me name this as the next state, okay. So these excitation tables is also called as the next state, okay. Now consider this feedback which is named as small y1, and there is number of variables over here, and let me name this as yn, and let me consider this as my secondary variables, okay, and these secondary variables can also be named as present state, okay. So we have already studied what is present state, next state, combinational circuit, all these variables in our past unit, that is sequential circuit, synchronous sequential circuit. So this is what is the basic block diagram of a asynchronous sequential circuit, okay. And we very well know that for a stable condition, our capital Yi must be equal to small yi. That signifies that our present state must be equal to next state. So whenever our present state is equal to the next state, we say that a system is in a stable condition, okay. So this is what is the block diagram specification of a asynchronous sequential circuit. Now let us go to the race condition. So I'll give you all the definition first and I'll explain what exactly is the race condition along with an example, okay. So race condition can be said, so let me write that first for you all. Race condition can be said to exist in an asynchronous sequential circuit when two or more, this is very important, when two or more binary state variables, change value in response to change in the input variable, change in an input variable. Dear students, just listen here. So the race condition can be said to exist in an asynchronous sequential circuit when two or more binary state variable change value in response to change in an input variable. So this is very important. So when this condition prevails, we say that the race condition exists, okay. So I shall explain you all with an example, okay. So in the race condition there are two types, okay. You should know about the non-critical race and the critical race. So let me tell you all about the non-critical race. Okay, so what exactly is the non-critical race? So non-critical race, that is, if the final stable state, let me write that, stable state, this is actually stable, the final stable state that the circuit reaches, does not depend on the order. This is very important. Does not depend upon the order in which the state variable changes. Okay. So this is what is a non-critical race. If the final stable state that the circuit reaches does not depend on the order in which the state variable changes. So here, this is very important. Here, it will not depend upon the order in which the state variable changes. Okay, I shall explain you all with an example so that you will understand the non-critical race. So let me take an example for you all to explain the non-critical race better. Okay, now consider this. So let me draw, or let me consider. So consider this block. Let me consider the present state as y1, y2, and let me consider the input x. So when I consider the input x, so it must be either 0 and it must be 1, right? So when I consider the present state as two variables, let me write the condition for you all: 0, 0, 0, 1, 1, 1, 1, 0. So I am writing something like this: 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, and 1, 1, 1, 1. So something of this sort exists. Now, as I told you before, for a system to be stable, your present state has to be equal to the next state. Okay. Now, considering a present state, for this present state, you can see when it is 0, 0, my next state is 0, 0, right? So this is something which is stable for me, correct? So you can just check out, is there any cases which is stable? Now here it is 1, 1. My present state is 1, 1, and you can see my next state is 1, 1. So this again is my stable state. So these are the two conditions which is stable for me, right? So none of other inputs gives me a stable state where my present state must be equal to my next state. So here my present state is equal to my next state, right? So this are the two inputs which gives me a stable condition. Now how will I check for the race condition? Okay, let me check for the race condition. Now consider the inputs. Say my present state, let me take it as 0, 0. Okay, so when I consider the input 0, 0, okay, this is my y1 and this is my y2. Okay, so if I'm changing, if my input changes by 1 bit, say my y1 is changing, sorry, my y2 is changing, so let me consider this as 0, 1. Okay, so if my input is changing by 1 bit, and here from 0, 0 to 0, 1 it changed. When it is changing like that, if at all there is a delay occurring in the system, once when the delay occurring in the system, this 0, 1 can become my next input, right? So you can see over here, when my 0, 1 becomes the next input, so for my condition 1 or for my input 1, I get a 1, 1, right? So I get a 1, 1. Okay, so let me consider another sequence. Okay, let me consider for 0, 0, again my input, my present state. So let me consider the change of my input, change of y1, when the input y1 changes to 1 and 0. So what happens here? So when the input changes to y and 0, and if there is a delay in the circuit that is existing, so this 1, 0 can become my another present state or another present state input, right? In that case, you can see that for my input 1, again my output is 1, 1, right? So here it again gives me a 1, 1, correct? So let me consider another sequence where my input is 0, 0, and let me consider my y1 and y2 is changing to 1 and 1. So once in the delay occurs, and when this 1 1 becomes the present state input, like you can see over here, so what exactly happens? For my input 1, you can see I am getting a stable state, that is 1 1, correct? So I'll get a 1 1 over here. So you can see that for all these cases, okay, you can see that I'm getting a stable cases, okay. So that is what is the non-critical race, right? It does not depend upon the order in which the state variables changes, but you get the correct or the orderly stable state. So this is what is the example for your non-critical race. Now let us go back to a critical race. Let us go back to the critical race. So I'll explain you all the critical race with the same example. Okay, you can consider the critical race. So critical race is something if the final stable state that the circuit reaches, depends on, okay, here this is important, depends on the order in which the state variable changes, okay. So here the final state variable that the circuit reaches depends upon the order in which the state variable changes. Here it depends upon the order, and in the non-critical race we saw that it does not depend upon the order. So let me consider the example for you all, so which will make you all understand the non-critical race. Okay, sorry, the critical race. Now consider this. So here, like the previous example, this one is a present state y1 and y2. My inputs 0 and 1. So 0 0 0 1 1 1 1 0. So let me consider 0 0 1 1 0 0 0 1. So 1 0 1 1 and 0 0 1 0. Now let me check out for my stable case. Here the input present state and the next state is same. So my stable state over here, 0 1 my present state and my next state is same. So I get a stable condition over here. My present state and the next state is same. So I get a stable state over here. 1 0 and 1 0. Okay. Now let me consider, or let me check for the race condition. Now I'll consider my 0 0, the input 0 0. Okay. So when I consider my 0 0, okay, so let me take a change in the input y1 and y2 as 1 1. When there is a delay occurring in 1 1, okay, which becomes an input, that is the next state input 1 1. So when it comes to 1 1, what happens is my output is 1 1, right? So my output is 1 1 over here. So the next case, okay, if I'm considering a 0 0, and let me consider a 0 1, okay. If I'm considering a 0 1 and if there is a delay in the circuit, this becomes my next input. So for 0 1, what happens? My output or my stable status is 0 1, right? Now consider another change of input when 0 0 condition where my y1 changes to 1 0. And if at all there is a delay, when this 1 0 becomes your next input, so I get the next condition as 1 0, right? So that is for the input 1. So you can see over here that your stable state is not correct, right? So it changes, okay? So critical race is due to the delay, and here what happens, it will end up in a wrong stable state. Understood? So in the previous example we saw that whenever the sequence changes by 1 bit, you will end up getting the correct stable state. But in case of your critical race, it will depend upon the order. Even though it depends upon the order, due to the delay element, it will end up in the wrong stable state, and that is what is your critical race. Dear students, hope you have understood the non-critical and critical race in detail. For any doubts, you can revert back to me. Thank you.